Hi and welcome to video 1 of 2 on Chapter 14. Now, Chapter 14 deals with inductance. And there are two basic types of inductance that we're going to discuss in this chapter. The first type of inductance is called mutual inductance. And just to sort of lay out the two, and then we'll talk about them in greater detail. With mutual inductance, what you have is a coil or some other circuit that has its associated magnetic field. And then nearby, perhaps you have another circuit or coil that has no current actively flowing through it. And what happens is through, we'll say circuit 1 here, you run your current through. So here's I running through. And what that does is to generate a magnetic field. So here's your magnetic field. It goes like this, forming a closed loop. Sort of a closed loop right there. Just kind of clean it up just a touch, so far as you can clean it up. Okay. So here, perhaps your magnetic field goes through like this, and obviously this is just one field line. And what happens is perhaps you vary the current with time, and what that does is to create a changing flux that goes through circuit 2 over here. And as a consequence, what you've done is you've induced a current, because you've created an EMF, via Faraday's law. So the other type of inductance that you see is something called self-inductance, which is generally what we just call inductance. And the way to get self-inductance is if you think about, for example, a circuit maybe that looks like this, where you have, maybe there's a battery attached to a resistor, and then there's a switch. So here, when you take and you close the switch, we know current is going to flow, in the conventional direction from positive to negative. And as it goes around the circuit, it builds from 0. And as a consequence, just due to the flow of current changing over time and building, what that does is to create a magnetic field that actually changes across the area of the circuit itself. So here, for example, we know, using the right-hand rule, that you would have, magnetic field changing in this direction right here. And so what's created is, as a consequence of this changing flux, is an oppositional current that goes back like this. Okay. So what that does is to actually take away a little bit from the current that's building, so it prolongs it. It causes a bit of a lag with respect to that. So what's happening here is this is doing it to itself. So that would be an example of self-inductance. And you can see the same thing with coils, for example, in a circuit where you have a loop. The minute you turn the current on, you have this, much stronger effect due to flux because you have more loops. And as a consequence, you have the oppositional current that's created. So that's self-inductance. Like I said, generally, it's been my experience that self-inductance is, we just call it an inductance. That's usually what's meant when if you were to go to the store and buy a coil and say, I need a coil that has this much inductance. They're talking about that. So what I'd like to do to begin with here is to talk about mutual inductance in greater detail. Then we'll jump over to self-inductance. And with mutual inductance, like I said, the idea is that you have a coil that has some sort of changing, current perhaps over time, And what that does is to cause EMF in a nearby circuit that lies just right to have the flux go through it. So like I said, I'm going to call this number 1 and this number 2. Now we know that EMF itself has a form that looks something like minus N d flux dt. Specifically when we're dealing with things that have more than one loop. So let's pretend that in this particular situation, circuit number 1 is the circuit that has a current that perhaps changes as a function of time, and as a consequence, that's going to create a magnetic field that changes as a function of time. Now we know the definition of flux relies upon magnetic field and also area. We're going to assume for the most part right now that our area is fixed. That's a good assumption to make. Excuse me. In general, in a circuit, that's absolutely true. So what drives the changing flux is the changing magnetic field. Now that said, if I were to look at the effect of this current right here, which I'll call I1, on circuit 2 over here, specifically through this coil of wire, the amount of flux that circuit 2 is going to experience due to the effect of 1 is going to depend in part upon the number of turns in my solenoid here, or my coil, that number 2 has. Now it's also going to depend upon the amount of current that's passing through number 1, because we know, for example, just looking at the magnetic field equation for a simple solenoid, which looks like mu naught, we'll say capital N I over L, where we know N over L typically is what we call lowercase n. It's the number of turns per unit length. Here, the amount of current is going to define, in part, proportionally, the amount of magnetic field. So this right here really is the relationship between the current in number 1 and the induced effects in number 2. And so what we do is we put an equal sign here. We put a constant proportionality, which is we call M, which is the mutual inductance. So N2, phi 2 1 would equal to M 2 1. That's our constant times I1. Now this also works in reverse. For example, let's pretend that it was coil number 2 that had the current flow running through it, which we'll call I2, and here perhaps coil number 1 over here in our circuit 1, perhaps there's no current flowing through it. So what happens is this produces an EMF in 1, which drives current. So you can make exactly the same sort of argument here, except now it would be the number of turns in 1 and the flux passing through 1 due to number 2 that would be proportional to the current flowing through number 2. And here, you would write your constant proportionality as M1, 2. It's the effect on 1 due to number 2, the effect on 1 due to number 2, so you can see the terminology here. Now, so to begin with, let's just take a look at the units here. M itself has units that look like, magnetic flux over current, if you solve for that. N itself here is a unitless thing. It's just the number of turns. Now, magnetic flux, remember, is measured in Webers, and current, we know, is measured in amperes. And this grouping of units right here is called a Henry, abbreviated H. Okay. So, much like capacitors, you see, capacitance on the order of 10 to the minus fifth, 10 to the minus sixth farads. Here, with a coil, you see, inductance, which is the property of a coil, we say. It's on the order of 10 to the minus fifth, 10 to the minus fourth, 10 to the minus sixth henries. Okay, so again, where you really what you're looking at is the effect of one circuit on another circuit, and it's this type of effect right here. It turns out that is what makes things like step up and step down transformers possible. Like for example, in your home, you have 240 volts of electricity coming in, and appropriate current to run your house. But out at the power pole, it's much greater than that typically. And what happens is you have these things that are called transformers, which basically look like a big paint can, that has some stuff sticking out of the top. And it's hooked to a power pole, and what it does is to help sort of manage some of the loss of carrying power through an electrical circuit by maintaining a high voltage. So so that's basically how it works, is by stepping down this high voltage to a lower voltage, and we'll be talking about how that works later on. Now, it turns out that this is sort of a duality thing. Okay, this constant proportionality right here, M21 or M12, they actually end up being the same, which is one of the reasons why you say it's mutual. The effect of coil 1 on coil 2 is mirrored in the effect of coil 2 on coil 1. All right, so mutual inductance is a very specific thing, and it's between things in the circuit. Now, you can relate, this stuff to the EMF that's been generated through this right here. So, for example, and I'm just going to drop the subscript M21 and M12 because, like I said, they're the same. So, for example, perhaps, into the flux, on 2 due to 1 is equal to M times, the current passing through 1. I could solve for, if I wanted, for flux here. And now when I look over here at how much EMF would be generated, this would be the EMF generated in circuit 2 due to, the effects of 1. Well, it's circuit 2 that we're talking about, with respect to how many loops it has. And then, you plug in, our flux. Like that. And so, the ends cancel because they're constants. The number of turns isn't something that's variable. And M itself is just a number. So M would come out, and you have a minus sign sitting out in front. And now you would have di1 dt. So one way of thinking about the amount of EMF that's being induced, by circuit 1 on circuit 2, would be that the EMF in number 2 is due to the mutual inductance that sits between the two and how the current in 1 changes with respect to time. So what I'd like to do now is just a quick example to show you how this works. The question I want to ask is what's the EMF induced in a circuit due to a coil with mutual inductance of 4.4 times 10 to the minus 4th henries if the current builds in the coil from 0 to 2.5 amps in 0.01 seconds. So, maybe you have some sort of circuit. I'll draw it, perhaps like this. It's a closed loop, just to make it interesting. Here's a resistor here, just to give us something to look at. So this right here would be our circuit that's going to have the induced EMF. Okay, I'll call this circuit number 1. And then, nearby, what we have is a coil. And coils and circuits are drawn. Let me just sort of draw a circuit here like this. They're drawn like this. So, maybe here's my battery source, my energy source right here. Oh, whoops. That worked out well, I guess. So, here's my battery source right here. And the way a coil is drawn, or an inductor is what we usually say, is just like this, just a loop of wire. Now, in reality, this would be oriented so this magnetic field can pass directly through this. Perhaps this would be sitting on the inside of a big coil, or sitting above it so the magnetic field that exits the coil can enter this. So the idea here is that we have, circuit 2, switch is closed. Perhaps we have current that slashes back and forth, with respect to time. We're going to assume, that we've closed the circuit and that our initial current here was 0, and our final current passing through our circuit is 2.5 amps. Now, it takes 0.01 seconds for it to build from 0 to that. We also have this mutual inductance that sits between the two, which is 4.4 times 10 to the minus 4th henries. So this is what we've been given. And what we're trying to find is the EMF that's been induced in circuit 1. So this would technically be associated right here with circuit 2. The mutual inductance is true for both of them, because it's mutual. It's something that's defined between the two. So what's the induced EMF? Well, it's pretty easy. EMF in number 1 is going to be equal to minus M times the change in current over time. And here, and this would be the change in current over time in circuit number 2. And here, since we're dealing with, initial and final results, we can sort of demote this differential, or this derivative rather, to displacements or changes in, if you want to think of it like that. So this would be minus 4.4 times 10 to the minus 4th henries. It would be 2.5 amps minus 0 amps divided by our change in time, which is 0.01 seconds. So how much EMF is induced here? Let's do the math. 4.4 times 10 to the minus 4th times 2.5 divided by 0.01. So 0.11 volts approximately. And there's a minus sign here reminding us once again about Lenz's law, which as stated we really don't have to worry so much about, since we just turned this thing on and we're letting it build in here. But even then, if the current builds in this direction right here, we can talk about the directions of the induced electric or magnetic field. So let's assume again that this is sort of lined up so that this magnetic field passes directly into it. Then as stated, the magnetic field here would come out and would go in. So you would have magnetic field going across. This would be also the direction of the changing magnetic field, because it builds from 0 and ends up ending up at 2.5 amps. And as a consequence, it creates changing magnetic field, right? So here, looking at the direction of the current flow here, it's gonna be this way. So the reason why is because if it's this way, then if you put your thumb in this direction right here and curl your fingers across, what you have is magnetic field that adds to the changing magnetic field on the inside and it violates Lenz's law. So here, our induced current is going to go this way, like that. So whatever EMF is being produced is driving that. Okay. So again, you can put the minus sign here. Typically, you don't. It's just there to remind us about what's going on and to be used in differential equations later on. So again, a pretty good example. Now, next I want to talk about self-inductance. Self-inductance looks more or less the same as what we have here, with respect to how it's defined. You have the number of turns, the flux through M, which is your mutual inductance, and I. Except here the I is due to the coil itself, and the flux is of the coil itself. The number of turns is of the coil itself. So differentiate between M, which is mutual, and the self-inductance. Generally what we do is we call it L. And so, just like, before, you have a relationship between the number of turns, the magnetic flux, and the current. L right here would be the self-inductance. So with the self-inductance, you can give it sort of the same treatment that you give mutual inductance. If you, again, solve for the magnetic flux as L times I over N, and then, use, the definition, or not the definition rather, but use Faraday's law, in this form right here. You can talk about the self-induced EMF. So if you plug this in here, the ends cancel, and you get basically, well, you get exactly the same equation as what you got, for mutual inductance, except now you have an L sitting out in front, and the change in current over time is actually the current that's going through the solenoid or through your coil. So that said, this is actually one of the ways that we can define inductance. L, and we usually use magnitudes for this because it doesn't make sense to have a negative inductance, and just because of directions and what have you. Again, this is sort of a reminder of, don't forget, Lenz's law. But if you solve for L, generally what you do is you write it, whoops, that's not a very good looking E. You write it this way, over di dt. So you just use absolute values to make sure that you end up with a positive number here for your self-inductance. So just as an example, what I'd like to do is to look at a solenoid. So we know coils have magnetic fields that are a function of the current that go through them, the length, and the number of turns, and the cross-sectional area they have. So we'll call it, we've already used L. We'll use cursive L for length. We have an area here, which I'll call A. There's the number of turns, which is N in our coil. And, perhaps there's, this much current running through it. Now, the thing is, what we have here, defining our self-inductance, you can also use this to find it as well. So this is equivalent as well. N times flux magnetic over I. Now, let's talk about our flux. we know in situations where you have changing magnetic fields and areas and stuff that that it's defined this way, right? Uh, but I'd like to consider a situation in which we've let this coil run current through itself until it builds a peak, so we have this constant flux going through. And in that situation, B comes out, and this ends up being just, B times the area. Okay. Now, what's the magnetic field? Well, it's a coil, and we know what the magnetic field due to a solenoid or coil is. It looks like mu naught, lowercase n, times I. Okay. So what that means is that the flux passing through, one of the openings of our solenoid here, due to the magnetic field that it has, is going to be mu naught times n, or lowercase n rather, times I times the area. Now I can take and plug this into this for the inductance. And when I do that, I have the number of turns. I have mu naught lowercase n I a over I, and the I cancels. Okay. Now let's not forget what n is. N is the number of turns per length. Okay, of my coil. So I can plug in for big N. Okay, for big N. Because big N, when you go to the store and you buy a solenoid or an inductor, we say, when you buy your inductor is bought based off of little n, and not off of big N generally. So if I solve for this, it's lowercase n times L. If I put that in for that, I have lowercase n times the length times mu naught lowercase n times a. Now you notice we have two here, two n's. Mu naught lowercase n squared. And then what I'm going to do is to pull the area and the length together right here. Okay, so this is a volume. Okay, that's what that is. That's the volume. And we can write it just as sort of capital V for volume. Now the important thing I'd like to point out here is that the inductance of this solenoid is purely a geometrical thing. Mu naught, is the permeability of free space. But n itself is the number of turns per unit length. It's a physical thing. It's not something that changes as a consequence of current flow or EMF or anything like that. It's a geometrical thing. Just like the area and the length of our solenoid are issues of geometry, right? So the volume there. So this right here should sort of draw an analogy in your head to something that we've seen that acts a lot like L. That would be capacitance. For parallel plate capacitors, that was epsilon naught A over D. Okay? It's a geometrical thing. It's based off of physical characteristics. This is based off of physical characteristics. So, one of the things that you'll discover about the various types of inductors is that invariably they're physical things. Okay, the inductance itself is like capacitance. It's based off of the physical properties of the inductor, and not how much current you pass through it, not how much EMF it has in it. So that's something to consider. Now, just as a simple example, here we have a coil that has 20 turns. It's 5 centimeters long, and it has a radius of 0.5 centimeters. What I want to know is what the self-inductance of it is. I also want to know that if current builds from 0 to 1.5 amps in it over a period of 5 seconds, how much induced EMF is going to be in there. So, what we're given here is the number of turns, the length, which is 5 centimeters or 0.05 meters. We're given the radius, which is 0.5 centimeters or 0.005 meters. We're given an initial current of 0, a final current of 1.5 amps, and an elapsed time of 0.05 seconds. And what we want to find here is the self-inductance and also the induced EMF. Okay. So really, L, like I mentioned, is mu naught lowercase n squared times the volume of our coil for a solenoid like this. Now, if I write this out, using the stuff that we have here, that would be capital N over L. The volume is going to be the length times the area. The area is going to be pi times r squared, because coils are like cylinders, right? So we just plug stuff in. It's pretty easy. This is 4 pi times 10 to the, is it 10 to the minus 7th Tesla meters per ampere? Let me check that real quick just to make sure. Yes, that's what it is. That's also a Henry per meter. Or Henry meter. Henry per meter? Yeah, Henry per meter. Let's see. N itself is 20. Our length is 0.05 meters. Square that. Our length again is 0.05 meters. We probably could have just canceled that, but hey, that's not that big of a deal. And R is 0.005 meters. We have to square that. So what's our self-inductance here? What's the inductance of this coil? 4 times pi times 10 to the minus 7th times 20 divided by 0.05 squared times 0.05 times pi times 0.005 squared. All right, so right here, this is going to be 7.9 about times 10 to the minus 7th henries. So here's our inductance right here. Now the next thing is what's the induced EMF? Well, we know the induced EMF is going to be minus L di dt. Or in this case, because we're given discrete points, minus L delta I over T, or 7.9 times 10 to the minus 7th henries, divided by, let's see, division rather there, 1.5 amps minus 0 divided by T, which is 0.05 seconds. So let's see, take that, multiply that by 1.5, then divide that by 0.05, and I end up with about 2.4 times 10 to the minus 5th volts. So there you go. So, there are a lot of parallels that we see here with respect to capacitance in terms of it being a geometrical thing. Now, one thing I would like to point out is that we could ask the question, how much energy is being stored inside of our coil. Now, to do that, what I like to do is to consider a situation in which you have a battery with a switch, with a coil like that. We use L for inductor. And so what I'm going to do is to turn the switch on and let this current start to flow through our coil. Now look, this coil is going to consume power. It's putting energy somewhere. We're going to see where it's at here in a moment. And so we also know, this being a series circuit, that the amount of voltage that sits across this coil, is going to be whatever sits here at the source. So if I want to talk about the amount of power that's being used here, it's just going to be I times V, right? It's the amount of current flowing through it times the voltage. Now, so what happens is this consumes power and it puts it somewhere else, which means that the place it's putting it would be negative. And so if you think about it, V here the way it's eating the energy up is through EMF, if you want to think of it like that. And well, no, let's not talk about this yet. So there you go. Pretty simple example. And in the next video, what I want to do is to talk about the energy stored inside a coil, and also talk about what happens when you start using inductors in circuits in combination with other components, like, for example, capacitors and resistors. And I'll see you then.